Ladies and gentlemen, I hope you're ready for the big bear of our parametric chapter tonight. Tonight's really going to be the kind of the peak and the climax of this chapter. And we're going to start to, last night we really mastered motion along a line where you had two options, left or right. Now we're going to incorporate motion in a two-dimensional plane. And that's what, and when I say curve, that's, I'll put a little note here, two-dimensional space. And we're going to call that a curve. And then when you get to calculus 3, and I'll kind of dangle the carrot here, so to speak, when you get to calc 3, now it's going to be motion within a three-dimensional space, and it's going to have that much more meaning and practicality to it. And whenever I talk about parametrics, I like to picture a nice warm summer day with a very friendly bee just buzzing carefree and aimlessly around. And that's the illustration I'm going to try to draw here is... let's say that maybe we'll say right there is our beginning point. That represents t equals 0. And this b, he's just kind of floating around. He's kind of buzzing this way and such, and maybe he takes off in this direction here. And we'll just throw a few arrows on here to represent his path as he meanders through the warm summer day. And again, parametrics are not bounded by the restriction of passing the vertical line test in order to be a function, so this one's perfectly fine. And today we're going to use this path a few times we're going to introduce vectors today. So those of you with a physics background are going to have a slight advantage, but I really truly think even if you've never sat in a physics classroom, you're going to be just fine today. And we're going to talk about the vertical component and the horizontal component a lot. For instance, if I happen to pick a specific moment here, maybe right here, at this moment he's doing a lot more horizontal traveling than he is vertical traveling. Vice versa, over here at point B, we'll say he's doing a lot more vertical traveling than he is horizontal traveling. And we'll get more in detail on that.
Shout out to the girls Jill Lutz and Alex Amagna.
Before we go any further, though, I want to do a super quick review of what we did 2 nights ago, and I want you to represent with great notation here. I want you to write down in your notebook the slope and aka the first derivative, and then the second derivative, which measures concavity. I want you to write those out. Hit the pause button. Come on back and see if you use the same notation I did to represent the first and second derivative. So here's what I came up with. For my slope, I said it's the rate at which y is changing with respect to time divided by the rate at which x is changing with respect to time. Certainly that simplifies to dy dx, which is rise over run. Now what we're going to do for concavity, and this is the funny one, what you're doing is you're taking your dy dx, which you already found, and you're differentiating that function with respect to time, and then you're just going to divide that by dx dt, which again is a quantity or a function that you already know. So how do we, in words, we describe that as the rate. Concavity is the rate at which the slope is changing with respect to x. And those are the two things you need to know from the other night. Now, with regards to what you need to know new today, this is the two most important definitions, and they're very simple. First of all, we're going to talk about what is dx dt and what does it measure and how do we describe it. Dx dt is the rate at which, you ever get the feeling that the word rate's pretty important? It's the rate at which the x-coordinate is changing with respect to time, okay? And then similarly, dy dt is the rate at which the y-coordinate is changing with respect to time. So those are the two biggies that we're going to hit on today, and we're going to gradually introduce a vector and show you how these all relate. Okay, I think the easiest way to introduce vectors is to imagine an oval racetrack, maybe a NASCAR track, and we'll say up here is the starting line. We'll say there's t equals 0. All the cars start up here, and then they travel clockwise around this track, and so forth. So what we're going to do is we're going to pick a few random points and try to draw the vectors and show you what's happening. Now, at this moment in time, when the cars are right here at point A, what's happening at that instantaneous moment is the car is doing more horizontal traveling than vertical, but it is doing a little of both. So as far as my horizontal vector is going to be significantly longer than the vertical vector. And notice I drew the vertical vector down because the height is slightly decreasing, and whereas the horizontal vector is moving to the right. And so what I would say at that one point, I would say that dx dt is certainly positive by a long shot because we're traveling to the right, yet dy dt is negative because we're moving down. All right, let's pick another point. Maybe let's pick this one right here. We'll call this point B. Now at that particular moment, we're doing probably more vertical movements than we are horizontal. But I think it's important to see that the vertical is going down, the horizontal is moving to the left now. And I would say, well, let's do dx dt first. Dx dt is now negative because we're traveling to the left. And then the dy dt is again negative because we're traveling down at that one instantaneous moment. And again, the length of that ray, or the length of the vector, describes, how aggressively we're moving in that particular direction. Let's go pick maybe point C right here. Call this C. Now in this case, my horizontal vector's very long, my vertical vector's quite short, and my C is kind of in the way. Make sure your horizontal is going to the left, your vertical is going up. We would describe dx dt as being negative because we're traveling to the left, and then we would say that dy dt is now, for the first time, positive because we're now traveling up. Alright, and that changed right around there. At that moment is when dy dt started being positive. By comparison, let's take a look at, let's call this D. And he's doing probably almost equal amounts of both at that moment. Maybe a little more horizontal than vertical. See if you guys agree, but they should be fairly almost congruent. And we'll say the horizontal vector is moving to the right, so our dx dt is positive, and also the vertical vector is moving up, so dy dt is also positive. So there's a brief intro to vectors and the horizontal and vertical component acting on a point at any time. Well, what I've attempted to do here on this next slide is I attempted to duplicate the B buzzing parametric curve to represent the path of the B. He started down here at t equals 0. And the first thing I want to do is I want to have a generic discussion about dx dt and when is he positive, when's he negative. I would say from t equals 0 until t equals some magical point right here, dx dt is positive. And then what happens is he starts traveling back to the left. So I would say from here until about right there, dx dt is negative. And then from that point forward, the B is now forever traveling to the right. So basically what we're saying here is the red represents when dx dt is positive, and the green represents when dx dt is negative. Alright, now let's switch gears and let's talk about dy dt, the rate at which y is changing. And this one is a little more interesting. First of all, starting at t equals 0, the dy dt is positive because right now the vertical component is going up. And then I would say right around there is when dy dt changes from positive to negative. And then, let's see if we can grab another color here. From that moment down to here, I would say dy dt is negative. When else is dy dt negative? I would say he's also negative from here down to here. And then again from here down to here. Alright, and just to finish it off, we could say that dy dt is positive. We'll start right here, and then he's positive all the way up. Start right here, and he's positive all the way up, and then again from here to here. So that's a breakdown. First we analyze just dx dt, and then we switch gears and analyze just dy dt. All right, the next thing I want to go over is the notation that we use. We have a very sharp bracket, and we say x of t comma y of t, and both of those represent functions. And that right there is what we call the position vector. So anytime you describe a vector, we should have these sharp brackets on the edge. Now, if we take the derivative of each one of them individually and said x prime of t comma y prime of t, we're now describing the velocity vector. Okay, and that's going to describe, that's the real important one. That's describing whether you're going up, down, left, right, and all sorts of in between. And then the third one, of course, is x double prime of t, y double prime of t, and I hope you've correctly predicted that, yes, this is the acceleration vector. And the big thing there is just to take away the notation. My next definition here, and this is worth putting a star next to it or a big box around it, it's kind of going to look like total distance traveled, except it's not going to have the integral on it. So if you take the quantity dx dt plus the quantity dy dt, and you wrap it up and you square them and you add them. Basically, it's the same thing as distance traveled or arc length minus the integral sign. This represents the speed of the particle at an instantaneous moment, or the speed is also sometimes described as the magnitude, or magnitude just means length of the velocity vector. Now basically what I was doing on that curve earlier was I was drawing an individual vector for dx dt and then an individual vector for dy dt. Now the velocity vector, and this goes back to something we did in Algebra 2, believe it or not. Let's see if we can try to generate a curve again here. We'll just draw something really random. Okay, so let's say I picked this particular moment right here. You've got a slight horizontal movement to the right, you've got a more drastic vertical movement down, and what you want to do is the velocity vector is going to kind of split the difference of those two, and it's going to kind of shade towards or favor the stronger of the two vectors. So in this particular instance, my velocity vector, change colors here so you can see it, my velocity vector is going to be about right there. And notice it's kind of in the middle, but it's going to favor the stronger of the two vectors a little bit. And so that vector right there represents the velocity, and the length of that vector, or aka the magnitude of that vector, is going to tell you the speed of the particle. It's going to tell you how fast it's moving. So in other words, the longer that these individual vectors are, then therefore the longer the velocity vector is going to be, therefore the faster the particle's moving at that time. Okay, here's our first example. We're going to run through 3 of them. This is a non-calculator example, and it basically describes a particle moves in the xy plane. There's your two-dimensional space. That's all that means. Okay, so that any time t, the position of the particle is given by, let's say, t cubed plus 4t squared. Okay, and the y of t is given by t to the 4th minus t cubed. Okay, now they want you to find the value of the velocity vector at t equals 1. So here's what you know about velocity. The velocity vector is dx dt, comma dy dt. On the earlier slide, I wrote x prime of t, comma y prime of t, and it's the same thing, just slightly different notation. So I'm going to say that the dx dt is really 3t squared plus 8t. All I did is I took a very simple derivative of that polynomial, comma 4t cubed minus 3t squared. So there is your generic velocity vector. Now if we want to evaluate that rascal at 1, all we're going to say, let's see, plug it in there, and 3 plus 8 is 11. And if I plug it in there, 4 minus 3 is 1. So right there, 11, 1 with the sharp brackets represents your velocity vector at t equals 1. And then the next thing they want us to do is to find the acceleration vector when t equals 2. Hey, no problem. The acceleration vector is going to be, all I'm going to do is I'm going to go back up here, I'm going to take their derivative, so it's 6t plus 8, comma, let's see, take his derivative, and that's 12t squared minus 6t. And now I'm going to evaluate that rascal at t equals 2. I think I'm going to get 12 plus 8 is 20, comma, oh boy, 12 times 4 is 48, 48 minus 12, 36 maybe? 20 comma 36. I hope I did the math right. So those are your two individual vectors at a specific moment in time. Again, we'll just, maybe the biggest thing is just getting used to the notation and the setup and making sure we've got these sharp brackets on the edges. Okay, number 2. Again, a particle moves in the xy plane. So all we're doing is, that means two-dimensional space. So that any time t, as long as t is greater than or equal to 0 for this one, the position of the particle is given by t squared plus 3t. And y of t is t cubed minus 3t squared. What they want here is the magnitude. That's, again, anytime you see the word magnitude, I want you to think of the word length. Length of that velocity vector when t equals 1. Now basically, I could delete that last sentence and basically go find speed at t equals 1. Okay, that's all they're asking for. When they say the magnitude of the velocity vector, all they're referring to is speed. So we'll start off with our formula, the generic formula for speed is the same formula that we use for arc length, except we just don't incorporate the integral sign, so it's going to be dx dt quantity squared plus dy dt quantity squared evaluated at the moment when t equals 1. So here we go. We're going to, and I'm going to introduce a slightly new notation here. Your dx dt is simply going to be 2t plus 3, okay, not earth-shattering there, I hope. Your dy dt is going to be 3t squared minus 6t. So we've got those squared, and here's the new notation. We're going to say evaluated at the moment when t equals 1, and I'd like to see everybody use that same notation in order to communicate the fact that we're evaluating it at the moment when t equals 1. So now we're just going to substitute that 1 into there, and let's see, this becomes 5 squared, which is 25. Let's see, 3 minus 6, negative 3 squared, we got a 9. Oh, what a fun number here. Radical 34 represents the speed of the particle at that moment, aka the length or magnitude of the velocity vector. Okay, number 3, kind of an interesting one to think through here. We're describing, again, a particle moving in the xy plane such that x is equal to radical 3 minus 4 cosine of t. So we're playing with some trig functions here. We'll make sure our calculator is in radian mode. And y is equal to 1 minus 2 sine of t. And I changed the notation just a little bit. You know, for instance, I didn't say x of t, but it certainly means the same thing. So over here, y of t, it's just the position vector. Where 0 is less than or equal to t, which is less than or equal to 2 pi. So that's our interval. We don't have to worry about anything outside that interval. Now, here's where it gets interesting. It says the path of this particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between those two x-intercepts. Now, just basic functions 101, regardless of whether it's parametric or rectangular or polar. When you cross the x-axis, one thing that you know to be true is that the y-coordinate, or the y value, is equal to 0. So all I got to do is I got to take that expression that I have for y of t, I'm going to set it equal to 0. We get that the sine of t is equal to 1/2. And there are two solutions for that within the interval 0 to 2 pi. One when t equals pi over 6, and then another one in the second quadrant when t equals 5 pi over 6. So those are the two moments where it crosses the x-axis, and now they're looking for the total distance traveled within that interval. And on parametrically speaking, total distance traveled is the exact same thing as arc length. So I'm just got to recall that formula. We're going to say that we're integrating from pi over 6 to 5 pi over 6. And then it's basically that speed expression, the dx dt squared plus dy dt. Now the one thing here that's different, when we were doing speed, we actually plugged numbers into these rascals here. I don't want to do that this time. I want to leave dx dt as a function of t, and same thing dy dt. I want to just leave it as a function, and we're really going to let the calculator take over from there if we needed to go any further. So we're not plugging any numbers into these expressions here, and that's my final answer. Our last one for the day, again, I didn't type it out ahead of time, but we will do setup only on this one again. We won't worry about evaluating, but basically they said the position of a particle at t equals 1 is represented by the vector 5, 7. So that's your position. So x equals 5 and y equals 7. And we know that the dx dt, or x prime of t, is 3t plus 1. They did not give us y prime of t. But now they're asking us, what is the x-coordinate at t equals 3. So what we're going to do is we're going to take advantage of the first fundamental theorem again. And generically speaking, if we integrated from t sub 1 to t sub 2, and we'd use the function dx of t, and we integrated with respect to t, you would get the position at t sub 2 minus the position at t sub 1. So basically this integral here, okay, that integral is measuring the change in the horizontal position. So let's just write, I think that's worth writing out. It's something that's going to pop up over and over again. It's the change in the particle's horizontal positioning. We're basically totally ignoring the y's. So up here, like that 7's completely irrelevant for this particular problem. So what I'm going to do here is I'm going to integrate from t equals 1, because that's what was given, until t equals 3, because that's what they're asking for. I'm going to integrate the function 3t plus 1 with respect to t, because that's the independent variable, and that's going to be equal to x of 3 minus x of 1. And one last little step, let's just add the x of 1 over. We know that, so we're adding a 5 over, and then we get the integral of 1 to 3t plus 1 dt, and that will tell you what x of 3 is. Now, is it possible to do that one by hand if they wanted me to? Could we evaluate this definite integral by hand? Certainly we could, but they didn't. Like I said, we were going to do setup only just to save a little bit of time, but I want you to know that we could go further if we had to. So there's our expression to represent x of 3. Good luck. This was our biggest lesson of the week by far, I thought, and tomorrow will be a great test for us.